Hello, hello. Today we will be discussing derivatives, both normal and partial. So let's get straight to it. So what is a derivative exactly? A derivative is, at its core, a way to figure out the slope of a tangent line to a function at any point. That is achieved by calculating the slope of a curve on a tiny interval. The formal definition perfectly illustrates that. However, it is quite complicated, so I'll not show it here. Look it up if you want. So how do we calculate a derivative? It is actually quite simple. You just have to remember a few basic rules. So I have the power rule on screen here. And so let's just go over what this is saying. So the derivative, and this thing right here is pronounced d over dx, or the derivative with respect to x, because as you can see right here, x is our variable. So this is pronounced d over dx of, not times. Don't get it confused with these brackets. This is not times. So d over dx of x to the n equals n times x to the n minus 1. So the derivative of x to a power n equals that power times x to that power minus 1. Fair enough. Moving on. The addition slash subtraction rule, again, plus or minus. So the derivative with respect to x of f of x plus or minus g of x equals the derivative with respect to x of f of x plus or minus the derivative with respect to x of g of x, where f of x and g of x are just any old functions that you learn in school: x squared, natural log of x, x plus 3, whatever, right? Then we have the constant multiple rule, where a right here is just any old number, right? 2, 3, 4, 100 quadrillion, whatever. Right? So this is read as d over dx of a times x equals a times x of d over dx of x, right? Pretty simple. Now, the natural log identity basically states that the derivative of a natural log is 1 over, well, should I say, d over dx of the natural log of x is equal to 1 over x, right? And a derivative of any constant number is just 0. So let's see some examples. So here we have d over dx of a times x to the n, where a and n are just constants, numbers, right? So let's apply the constant multiple rule, right? We take out a right here, so a times d over dx of x to the power of n, and then apply the power rule, so we get a times n times x to the n minus 1. Notice that this is the same thing we discussed like in previous slides when I showed you the formulas, right? So yeah, it's really that simple. Let's try with some numbers. So as you can see, d over dx of 4 times x to the third. As you can see, a equals 4 and n equals 3 in this case. So first, let's take the constant out. 4 times d over dx of x to the third. Again, same thing that we saw in the previous slide. Then let's apply the power rule. 4 times 3 times x to the 3 minus 1, and then simplify, because we all know that 4 times 3 equals 12, and 3 minus 1 equals 2. So yeah, we're done. Moving on, the d over dx of the natural log of x. Here we just use the identity of derivatives, right? So like d over dx of the natural log of x equals 1 over x. So does this make sense graphically? Well, let's see. I have pulled up a graph of this function on the next slide. So according to that derivative from the previous slide, we know that, for example, the slope of the tangent line, and I hope that all of you are familiar with what a tangent line is. A tangent line is basically a line that approximates the function best at any point, right? So, for example, at 1, the derivative says that the slope should be 1. On the graph, I have drew this tangent line right here. So, is the slope of this thing 1? Well, it kind of looks like it, but we can use a rise over run here, right? Let me just find this point, for example. So yeah, rise is 1, run is 1. Sure looks like this thing has a slope of 1, right? And 1 over 1 is 1, right? Then at 2, this thing should have a slope of 2. Let's see if it does. Approximately right here, maybe. So rise 1, run 2. Obviously, I have not drawn this perfectly, right? But it looks like it does have a slope of 1 over 2, or 1/2. Then at 3, we should have a slope of 1/3. Rise 1, run 3. Yeah, sure looks like it. And then, for example, at 1/2, right? At x equals 1/2, we should have a slope of 2 because 1 over 1/2 is just 2. So rise equals 2 when run equals 1. Rise over run gives us 2. So it does make sense. That's great. Obviously, this is not a rigorous proof by any means, but this can just give you the intuition a bit. Okay, so moving on to part 2, partial or multivariable derivatives. That's actually what I prefer to call them, because partial isn't really that intuitive. So what is a partial derivative? A partial derivative is basically the same as a normal single variable derivative, just where one or more variables is considered a constant. This follows the same basic rules as a single variable derivative, which is nice because we have already discussed them. Like everything, it is easier to work through some examples to understand what I mean. Examples. Sorry. So, and a partial derivative is denoted or written with this weird backwards curly D that also looks like a 6 backwards. No idea what language that came from. So, partial x, that's how it's pronounced, or the partial derivative with respect to x of x to the alpha times y to the beta, where alpha and beta are just numbers. Because this is a derivative with respect to x, we will consider y a constant. Might be a bit unintuitive, but when we take a derivative with respect to x, that means that only x is changing. Therefore, y is our constant, right? Fair enough. So if it helps, replace y to the beta with any number. I'll do 2 for simplicity. So partial x of x to the alpha times y, where alpha is just a number. So let's take the constant out, 2 times partial x of x to the alpha, then apply the power rule again, what we saw in the single variable case. Now, remember the previous slide, we set y to the beta to be 2. So let's substitute back, 2 equals y to the beta. And we get y to the beta times alpha times x to the alpha minus 1. Right? Let's actually try this with some numbers. So right, partial x of x squared times y to the third. Since we're differentiating with respect to x, we consider y a number. Again, a number raised to the power of another number, 3 in this case, is also a number, so we just take it out by the constant multiple rule. Y to the third times partial x of x squared, then apply the power rule. Y to the third times 2 times x minus 1, and this can be simplified a bit when we subtract this right here, right? And just put it in order, right? Same order that you learned in school. Now, let's try differentiating the same thing with respect to y. So here x is the constant. So let's take out the constant, which is x squared. So x squared times partial y of y to the third, then apply the power rule, x squared times 3 times y to the 3 minus 1. Again, same thing, do the subtraction, rearrange, then we get 3x squared y squared. Fair enough. Now, let's look at this beast of a derivative. I promise it's not that hard. The only thing you have to notice here is that a and alpha are not the same thing. A is from the English alphabet, or the Latin alphabet to be completely precise, and alpha, this thing, this A with an extra thing right here, is from the Greek alphabet. Right? So again, partial x of a x to the alpha plus b y to the beta, right? Where all these are just numbers. Fair enough. Now let's apply the addition rule. We have went over that when we discussed the rules again. Right, so partial x of ax to the alpha plus partial x of by to the beta. Then we use the identity that a derivative of any constant is 0, right? Fair enough. So this thing right here, this whole thing just goes to 0, which is really helpful because we do not have to calculate this big thing. And we only have to calculate this fairly small thing, actually. So let's take the constant out, a times partial x of x to the alpha. Then apply the power rule. Notice again that this is a and this is alpha, not the same thing. We cannot rewrite this as a squared or alpha squared. No, it's bad. So a times alpha times x to the alpha minus 1, right? And then let's do the same thing with respect to y, right? So partial y of the same good old expression, if I could only find my mouse. So right, partial y times a x to the alpha plus by to the beta. Apply the addition rule, same thing. X is like a constant. Then derivative of a constant equals 0 identity. This whole thing right here just goes to 0. Then take the constant out, which is our b right here. And then just apply the power rule. Simple enough. Right? B times beta times y beta minus 1. And it's a good thing that b and beta aren't so easy to confuse. Okay, well, fair enough, but b, uppercase B, and beta are pretty easy to confuse. I'll give you that. So, well, yeah, that's really it. Of course, single and multivariable calculus are big fat subjects, but now that we got the basics down, we can do anything. See you in class.